All right, talking about advanced aerodynamics here on this worksheet. So talking about how power required curve is going to change during different phases of flight. During climb out, the power required curve is going to increase because of that. The aircraft is going to need more power to overcome gravity and the higher induced drag because of the increasing low attack, and also the higher parasitic drag due to the increased true airspeed. During cruise, the power curve required is going to decrease because the air density decreases, decreasing the parasitic and the induced drag. During descent and landing, curve shifts upward again because of the induced drag of configuration changes like flaps and gear, and requirements like speed and altitude limitations we have to make as we descend for approach. The implications of these changes, how they're going to affect forward airspeed, maximum endurance, and best endurance. So climb out's typically going to limit maximum forward airspeed because you have the induced drag and you're climbing against gravity, right? At cruise altitude, you're going to reduce that drag by lowering the angle of attack, and you're going to allow the aircraft to achieve its highest forward speed efficiently. During that descent and landing, various factors is going to affect it depending on the configuration and the speeds that are required. Maximum endurance is going to be reduced during climb out because of that high fuel consumption, like we talked about, high angle of attack and high power setting to climb. And this can be optimizing cruise. That's going to be your best endurance, is get a cruise, like a long-range cruise speed because of the lower fuel consumption with the thinner air. And then best endurance is going to suffer the most during climb out because of that increased drag. It's going to be, the endurance is going to improve in cruise, and it's going to be reduced. It's going to be less important as we descend to land because we're descending to land. We're no longer worrying about being up in the air for as long as possible. The relationship between range and endurance, pretty simple. Range is the distance that you can fly with fuel. Endurance is the time you can fly and stay airborne with that fuel. So they are related. Optimizing one isn't going to necessarily mean that the other one's going to be optimized as well, because one's time and one is distance, right? So there is a speed at which you can reach, the best of both of those, but it's not going to be optimizing one specifically over another. Balanced field diagram here that I wrote, that I drew up and imported here into the document here. Critical failure point is A. That is this point right here. That's the point where it's critical if you have a failure because you either need to continue or abort it right there. Beyond this point, it might not be possible to stop on the runway. You'll see that it also coincides with V1, which is something we'll talk about here in just a minute. B is accelerate all engines. So this is, if you have both engines, you continue that acceleration. Sorry, son here. Ahorita vamos, estoy hablando. Accelerate all engines. The point indicates the speed at which all engines are operating, providing maximum thrust to accelerate the aircraft for takeoff, and marks the beginning of the takeoff roll. Accelerate one engine out. That's going to be this dash line. If you lose an engine, that power curve dips a little bit. This is going to be in case of an engine failure. This is where the aircraft can safely continue to take off on the remaining engines. Ensures the aircraft to still reach a speed where it can safely climb and take off. D, decelerate. This is this curve right here. So the decelerate line here marks the point where the aircraft reaches decision speed and must continue to take off even if the engine fails. Beyond this point, the aircraft is committed to take off, and any failures require handling in the air. V2 here, this next line, is going to be the takeoff safety speed, which is the minimum speed at which you can continue to take off safely after an engine failure. So assuming it's climbing at the engine climb out gradient. V1 is that decision speed that we talked about. You get to V1, that's where you make the decision, continue or stop, right? Make that decision prior to V1. V1, you must continue and take that into the air. Balanced field length is the total length of the runway needed for takeoff when where the accelerate stop distance is equal to the accelerate go distance. Its balanced field length ensures that the aircraft can safely continue to take off or stop within the available runway length depending on the situation.